Hello everyone, my name is Zhendong Wang. I'm from UT Dallas. It's my great pleasure to present our work, Understanding and Tackling the Hidden Memory Latency for Edge-based Heterogeneous Platform and HotEdge 20. Firstly, I will introduce the background, then I will explain the motivation and challenges. Third, I will demonstrate our core design. And finally, I will evaluate and conclude our work. Nowadays, the machine learning application, especially the DN-based applications, have enabled the autonomous machines to be deployed in the edge computing scenarios. These edge computing applications are typically deployed in the integrated CPU and GPU platforms. Even so, the deployment in the iGPU platforms are stymied. Firstly, these platforms have very limited memory space. For example, the TS2 only have 8 gigabytes. Secondly, these applications are typically safety critical and latency sensitive. They impose stringent requirements on the latency processing in the iGPU platform. Therefore, the unified memory management model is introduced. The unified memory model provides a shared virtual memory space between the CPU and GPU. The UM model can ease the memory management and free the programmer from the complicated memory management. Unlike the conventional copy then execute model, the CPU has to allocate memory space for the data in both the CPU side and the GPU side. In UM model, the CPU only allocates one memory region for the data, which can be shared by the CPU and the GPU. Therefore, the memory footprint can be reduced. In CUDA programming, the API CUDA malloc managed corresponds to the UM memory allocation. Even so, I wondered whether the current UM model is good enough. No, the answer is no. We have found that the current UM model has some hidden latency, which can prevent the deployment of these applications. We'll explore the hidden latency. I first explain the data processing data flow under the default model and the UM model. Here, the default indicates the conventional copy, the execute memory model. UM indicates the unified memory model. In default model, the CPU allocates memory space and then initiates the data. Later, the initialized data is copied from CPU side to GPU side for computation. After the computation, the results are copied back to the CPU side. Under UM model, the CPU first allocates memory space and initializes data. There is no data copy. The data is directly mapped from the CPU side to the GPU side. Since we target the autonomous driving workloads, these workloads typically involve large matrix operation scale, such as the matrix addition and the matrix multiplication. I will use the two representative workloads to illustrate the hidden latency. I break down the two workloads implementation into two parts, the initialization part and the other part. The initialization indicates the data initialization, that is the process of assigning specific values to the variables. The other part includes the H2D copy, D2H copy, and the kernel time. For UM model, there is no data copy. Therefore, the other part only includes the kernel time. And the two fingers shows the red bar indicates the other part, and the green bar indicates the initialization part. Obviously, the initialization causes great latency. Under UM model, the initialization even contributes up to 90% to the overall latency. Therefore, we can see that the current UM model spends extensive time on the data initialization in the CPU side. Meanwhile, we compare the kernel time under the default model and the UM model. The red bar indicates the default kernel and the green bar indicates the UM model. We can see that the UM kernel has much larger latency than the default kernel. And we discussed about under UM model, the data has to be mapped from the CPU side to the GPU side. The mapping latency is included in the kernel time. Based on the observations, we can conclude that the current UM model initializes data in the CPU side. Actually, it is not unnecessary at all. We consider moving the data initialization from the CPU side to the GPU side to save the latency. This may also benefit the following kernel execution and the overall application response time. Therefore, in our design, we propose the enhanced unified memory management model. The eUMM model has initialized data in the GPU side. Shown and the finger in the bottom. First, the CPU allocates data in the CPU side. This time, data is populating in the CPU side. Then, the page is carrying the data. It's mapped from the CPU side and then remapped to the GPU side. Later, an initialization kernel is launched in the GPU side to initialize the data. Finally, the real execution kernel will implement execution on the data. Meanwhile, we apply the prefetch and CUDA streams in the GPU initialization scheme to further reduce the latency. In the present GPU initialization, all the data has to be mapped from the CPU side to the GPU before the initialization kernel. With the prefetch applied, we divide the data into different tiers. Therefore, the mapping of different tiers of data can be overlapped with the initialization of different tiers of data. As a result, the overall mapping and the initialization latency is reduced. Fourth, we evaluate our design in NVIDIA TX2 and the HAX platform. We use four benchmarks, the matrix addition, matrix multiplication, NW, and RA. Firstly, we compare the data initialization performance. The red line indicates the GPU initialization in the eUMM model. The green line indicates the CPU initialization in the UM model. For the most benchmarks, the GPU initialization can outperform the CPU initialization if the data size is large enough. This is because the GPU's computation capability can be fully exploited if the data size is large. Meanwhile, we can observe that the GPU initialization possesses some inherent latency if the data size is small. This is because the GPU initialization is a kernel which has to be launched from CPU side. This causes some unavoidable latency. For the benchmark NW, even though the input size is small, the CPU initialization is still larger than the GPU initialization. This is because the input size of NW cannot be less than the 16 times 16, which is the minimal limit. We speculate that if the data size can be further reduced, the CPU initialization latency will be less than the GPU initialization latency. Then we compare the kernel latency under UM model and eUMM model. As you can see, the red line indicates the kernel under eUMM model and the green line indicates the kernel under UM model. Obviously, the eUMM model kernel can reduce latency from the kernel under UM model. And we discussed about the mapping latency is saved from the kernel under eUMM model. Finally, I will conclude our work that we have characterized the hidden latency in current UM model, the initialization latency, as well as the latency in the kernel launch. Therefore, we developed the enhanced unified memory management model, which can initialize data in the GPU side. Also, the prefetch and the CUDA streams are applied in eUMM model to further reduce the initialization latency. In the future, we plan to extend the eUMM model to a broad spectrum of workloads. Also, we will plan to reduce the inherent overhead of GPU-side data initialization. If you have any question, please feel free to contact me.